Morning, everyone. Welcome to day 27 of Math 133. We are near the end. Um, so today we're going to cover the Chapter 11 project, which is on page 578 in your course pack. Don't forget to do the 11.3 lecture notes and the Chapter 11 flow chart lecture notes. And these are your last lecture notes. So on Thursday this week, we're going to cover the Chapter 11 review. And then next week, we're going to be getting ready for the final exam. Final exam on December 11th. So very similar to the midterm exam. You can take it at the testing center or you can take it with me on Zoom. Um, so uh, make sure you definitely get the flow chart lecture notes done because those you're allowed to have in the final exam with you as well. So those are going to be important. Um, okay. So today for the Chapter 11 project, it's on page 578. Also, if you click on the Chapter 11 project here in uh, Canvas, um, there's two links. They're going to take you to StatCrunch. One is for confidence levels, and one is for levels of significance. Okay, so I'll need both of those as well. Um, all right, but we're going to start on page 578. There we go. And so this is our Chapter 11 project where we're going to talk about M&Ms and Skittles together. So Chapter 11 is all about comparing two populations, okay, and trying to figure out or sorry, two samples, and trying to figure out if they're from the same population or if the two populations are different, okay. Um, so uh, Here we've got our M&Ms and our Skittles, and we're going to try to look at the proportion of colors for each of the two different populations. Okay. Um, all right. Uh, Fill out the table with the total number of candies in the whole bag. So now we finally get to talk about why we needed you to make sure that you bought Skittles that matched the same colors as your M&Ms because we are going to look at, okay, how many green M&Ms did you have? How many green Skittles did you have? What's the proportion? And then what's the difference in green versus orange versus red and yellow? So they only match with the four colors, right? M&M's has blue and brown, but there's no blue and brown Skittles. There are blue ones in the like in the wild berry ones, I guess, but there's no brown ones as far as I know. I don't even know what flavor brown would be. That'd be gross. So I'm gonna need my data that I collected on my Skittles and my M&Ms. Um, so first of all, my N1 is how many M&Ms I had total. Okay. So for me, I had 145. And then I had 22 green, 29 orange, 17 red. These are not in alphabetical order. That's annoying. And 28 yellow, or in any order, it looks like. Okay. So just make sure you write them in the right order. Um, so now that I've got that, I can calculate my proportion of M&Ms. So what percent of my M&Ms were green, orange, red, yellow. So remember that p hat is x divided by n, so I need to do 22 divided by 145, and then 29 divided by 145, and so on and so forth. Um, and I'm lazy, so I'm going to do this in Sheets. So if you go to Google Sheets and you click on this plus for a blank spreadsheet here, so I can put in my numbers for M&Ms and so on. So green, orange, red, yellow. Because now I can do the proportion, and so it's equals, and I can click on this cell and then divide by 145. And yep, there's all my proportions for my M&Ms. All right, so green was 0.152, 0.200. Okay. And then for my Skittles, let's see, I had 51 green, 54 orange, 47 red, and yellow was 55, and my total is 241. Now, make sure you use the total of all Skittles, including purple, okay, even though there's no purple M&Ms, because we don't want to just count these four, okay? I mean, you don't have that sum anyway, but here's my N2 basically. So 241. And now I gotta put in those numbers in here for Skittles. So I had 51. So I can do equals this one divided by my total. All right, so my p hat for Skittles now is, okay, all right. So the difference now is we take PM minus PS, okay? So some of these might end up being negative, okay? Um, so make sure that if it's positive or negative, make sure you put the right sign there, okay? All right. So to do that over here in Sheets, I do equals. I want to subtract the proportion for M&Ms, which is this one, minus subtract the proportion for Skittles, which is this one. And there we go. I mean, you could just do those in the calculator if you want. It's just faster to do it in Sheets, I think. 0, 5, nope, not 059, 060. That one's negative. This one's going to be negative as well. 024. 8, 035. Okay. Circle the color that had the largest difference in proportions between M&Ms and Skittles. So basically ignore the plus or minus and just look for the largest number. So this one was 6% for me, 2%, 7%, 3%. So mine was red. Red had the biggest difference. Okay. Circle the color that showed the second largest difference. Mine would have been green. Okay. So it looks like we'll use red for part 4, and I'll use green for parts 2 and 3. So we're going to use the second largest one first. Okay. So for me, that's going to be green. So obviously it's going to be different for you guys, but Let's go on to the next page, page 579. Use the StatCrunch file to generate two different random confidence levels. Use data sample, then select size of 2. All right. So we need two confidence levels. So back over here in Canvas, if you click on the Chapter 11 project, there's a link here that'll take you to StatCrunch random confidence level file, which is going to be this one. So the confidence levels are going to go from 70 all the way up to like 99%. Confidence levels, you'll remember, are large, okay? Like 99%, 95%, 90%, okay? So I need to pick one of these at random, no, two of them. So I'll do data, sample, and then I need to click on that one and I'll do a sample size of 2, hit compute, and it's going to give me two random confidence levels. My first one is 86.3%, and my other one is 76.3%. Okay, and I'll write those here. Okay, now yours are going to be different because it's random, doing a random confidence level. Okay, next, use this one for levels of significance to generate a random level of significance. Same thing, except we're going to get a sample of one. And levels of significance, you remember that's our alpha. And these two are related. Confidence level and level of significance are going to add up to 100%. Okay. So if my confidence level is 86%, then my alpha in that case would be like 14%. Okay. So but you're going to use the second link here, random levels of significance file, which is going to be this one. And remember that your alphas, your level of significance, is a small number. So this is 10%, 5%, 1%. Okay. And we're going to select one of these at random. So data, sample, level of significance, and we'll do a sample size of just 1. And mine is pretty small, 1.7%, 0.017. Okay. All right. So we're gonna use this one for comparing M&Ms versus Skittles. We'll use this one for sample sizes, and then we'll use this one for hypothesis testing. Okay. All right. First confidence interval for M&Ms versus Skittles. You want to construct a confidence interval for the difference in proportion of M&Ms and Skittles for the second largest difference color. So for me, that was green. So from number three for me, I circled green. Verify whether all the requirements are satisfied for constructing this confidence interval. Okay. All right. So all the stuff that we're going to cover today for looking at two proportions. So we have M&Ms and Skittles, and we subtract them. We're trying to compare the two different populations. All of that is going to be on page 264. Okay. Um, and this is going to be if we're doing hypothesis testing. Okay. But it's the same StatCrunch. So stat, proportion stats, to sample with summary. It's the same StatCrunch for confidence intervals. Okay. And it's going to be the same requirements to conduct the test versus build the confidence interval. Okay. So basically, what are we trying to do here? So M&Ms, we have these proportions that we've collected. And these are approximate proportions for the entire population of all M&Ms. Okay. Now we know that there's 6 colors of M&Ms, so we don't technically know the true value of p hat, but we can guess that it's probably 1/6. 1/6 of all M&Ms are each different color. They produce the same amount of each one, okay? 1/6 is 16%. 16, 0.1667, right? Skittles, on the other hand, there's only 5 colors, and so all the proportions are going to be close to 1 out of 5, which is 20%, okay? So we want to compare and say, okay, are the two proportions the same? Now we know, because we're using M&Ms and Skittles, because we're using candy, that the two proportions are not the same, okay? So there's a difference between them that's not 0. There's a difference where this one, 16% minus 20%, is 4%, negative 4%. So all of these values are somewhere around that, okay? So we know that there's a difference between the two populations. How big of a difference is it? That's what the confidence interval is. It's going to measure approximately how big of a difference it is between these two populations, okay? All right. So before we can build that confidence interval, we have to verify that we have satisfied the central limit theorem. And it's a little more, there's a few more steps when you're looking at two populations at the same time, okay? So we still have to check random, and it has to be random for both samples, okay? We have to also verify that the samples are independent of each other, and the samples are independent of the population. And we have to check both of them, okay? So we do 5% of this population, 5% of this population, which again, you can write as 20n is less than capital N, or and 20n2 is less than capital N2, okay? And lastly, we have to check that NPQ is bigger than 10 for both of them, okay? All right. So first of all, random, okay? So yes, every M&M and Skittle had equal chance of being selected, right? Right? We didn't purposely go out and pick our M&Ms or our Skittles. We just grabbed a random bag off the shelf, so they are random. Next, independent. Okay. So what I mean by independent here is when you're measuring two populations or two groups, okay, you might be measuring a single population, which is fine. When you're measuring uh, and comparing two different samples to each other, there's two ways you can do it. One way is you take a sample, test everyone, wait a little bit, and test that exact same sample again. That's a dependent example. And in that case, you have one group, one sample, measured twice. Okay. That's not what we have here. Okay. What we have here is we have two different samples measured once. Okay. Both of those are valid. Okay. And in this case, I'm going to write two groups measured once. Okay. So as long as both samples don't share any individuals, okay? So what I mean by that is um, we don't have an M&M that's in our M&M bag and also in our Skittles bag. I mean, that can't exist, right? M&Ms don't show up in your Skittles bag. If you ever get an M&M in your Skittles bag, like I wouldn't eat that. Um, so they are completely separate. Okay. So this one is obvious because, like I said, M&Ms are never going to show up in your Skittles bag. But if I was sampling like people and I was measuring, okay, I'm trying to see which of these two COVID vaccines is more effective, right? Back when COVID started, there was a Pfizer one, and then there was I don't remember the other one, but there it started with an M, but there were two shots you could get, and which one was more effective. If I wanted to measure that, I would need to take a sample of all the people in the US, okay, and give a shot of the Pfizer to some people and the shot of the other to the other group, okay? As long as those two samples don't share any people. Because if you had a person who was in both samples, that'd mean they'd be getting both shots. And if that person, didn't get COVID, you don't know which of those shots prevented it, which of those shots was more effective because they got both of them. Okay. So it messes things up. So when you're measuring two samples, the two groups need to be completely independent of each other. Okay. Or they need to be dependent, meaning the exact same people are in both groups. Okay. So in that case, uh, if we were measuring like, okay, we're going to give them the shot and then you have to do a booster later, we need to make sure that all the people who got the first shot also get the booster. Otherwise, if you have someone who just gets the single shot and doesn't get the booster, then you don't know whether that booster was effective or not because some people didn't get it. Okay. So, anyway, we'll talk a little bit more about that when we look at the Chapter 11 review. But for now, the two answers you can put here are two groups measured once or one group measured twice. And we have this one, so we are good. But we also need to check that the two are independent of the populations. Okay. And that's what we've done before, right? We look at 20 times n is less than capital N, right? Except I have two different populations, so I need to do that twice, okay? Now, sometimes your N1 for your populations are the same. It could be, all US adults, like I said, when I'm testing two different COVID vaccines. In this case, they're not the same, right? This one is all M&Ms, this one's all Skittles, okay? But that's fine. I had 145 M&Ms, and I had 241 Skittles. So let's see. This is uh, 290, and that is less than all M&Ms, so we're good there. And then this one is 4,820, and that is less than the number of Skittles. So both of those are good. So yes. Okay. All right. Next, I need to check that both these are coming from normal populations. So NPQ has to be greater than 10. And again, I'm going to check that for both samples. So you don't have to write 1 if you don't want. You could write M for M&Ms, and then N, S, P for Skittles, and Q for Skittles. Okay. I mean, you could just write NPQ. It's just that you need to keep track of, okay, I did this for M&Ms and I got to do it for Skittles. So for M&Ms, I had 145 M&Ms. I am looking at the green M&Ms because I circled that for number 3. So my P is 0.152 for green. That makes my Q, let's see, 1 minus 0.152. 0.848. So if I do 145 times 0.152 times 0.848, I get 18. So that's greater than 10, so I'm good there, but I also need to check it for Skittles. Okay, so I had 241 Skittles, still looking at green. So that makes my Q for green 0.788. So 241 at 40, which is bigger than 10. So yes, I got two yeses there. So we're good. All right. If you got a no, if you got one of these as a no, then the whole thing is a no. Okay. You would, in that case, you would need to go back and you would need to select a bigger sample. Okay. Now, if you ever run into that situation where you're like, oh shoot, I don't have a big enough sample, are you allowed to, do you have to restart or can you use, you know, part of your M&Ms and then, just go buy a bigger bag and mix them together? The answer is that as long as the first bag was random, and as long as the second bag is random, when you mix them together, random plus random is still random. So, um, that's important because, like, if you have to go back and buy a new bag, like that's going to cost you money. Or if you had to, redo your sample, you have to go back and, you know, talk to more people. That's going to take time. It might cost money. But as long as your first selection was random, you can still use it. Okay, you don't have to restart. But anyway, hopefully we got a couple yeses. Even if you didn't, that's fine, regardless of whether the requirements were met in number six. Okay, so in practice, if we get a no, we would stop there and we would need to go make a bigger sample. Okay, but in this case, even if you did get a no, we'll just push on. Construct a confidence interval for the difference in proportions of your chosen color for M&Ms and Skittles using confidence level number one. My confidence level number one was 86.3%. Okay, yours is going to be different. That's fine. Okay. We don't need to show our work because there's a lot of work. There's a formula, right? There's substitute in, and then you have your result. But all of that, we're going to skip over and we're just going to do it in StatCrunch, okay? So stat, proportion stats, to sample with summary, okay? So come over here, sign into StatCrunch, and then once you've signed in at statcrunch.com, you can click this orange button right here to open up StatCrunch, and we'll go stat, proportion stats, to sample with summary. Okay. Now, most of the time we've been doing one sample, right? Two sample is all the stuff in chapter 11 where we've selected two samples and we're comparing them. Here we've selected a sample of M&Ms and a sample of Skittles. Okay. Uh, with summary. Okay. So for M&Ms, uh, I'm still doing green. We're still doing the one from number three. I had 22 green out of 145. For Skittles, for green, I had 51 out of 241. So if I was doing hypothesis testing, which we will do in a little bit in this project, I make sure I keep this button checked. But I don't want that. I want a confidence interval. So I'm going to come down here and click that. And we'll do the level from page two. I had 0.867. Okay. And we'll hit compute. I didn't select show critical value. That's okay. I don't need it here. I just need the upper limit and lower limit. My lower limit is negative 0.11. How many? 5 decimal places? Oh my goodness. 0.11961. And my upper limit, wow, my upper limit is real close to zero. 0.00018. All right. So there we go. So what does this mean? So this means that if I was to compare the proportion of green M&Ms for the entire population, all M&Ms, which I can't measure, okay? But if I was to measure that whole thing, and then I compared the proportion of green Skittles, and I subtracted them, I would get some number, okay? That number is not zero, okay? Or maybe it is, but it's going to fall somewhere in this range. I am 86.7% confident. I'm 86% confident it's going to fall somewhere in this range, okay? Now, we actually know the answer in this case because we know that the M&M and M and the Skittle company, they're producing the same amount of each color. So we actually know that 1/6 minus 1/5, how much does that come out to? 1/6 of all M&Ms are green minus 1/5 of all M&Ms are green, or sorry, of all Skittles are green. So the true value is 3%, okay? Negative 0.3, okay? And you'll notice that that number does fall in my range. So that's good, okay? Now we don't if we were looking at something else, like we were comparing, you know, effectiveness of COVID vaccines, we don't know that true value because we can't test the entire population. We can't, give the Pfizer vaccine to every single person, partly because, some people don't want it, but also like, you know, that's a lot. It's going to take a lot of time, and so in that case, we don't know the true proportion, but we can at least use our samples to say, okay, it's going to fall somewhere in this range. Okay. Okay. Now, if the two proportions were the same, okay, so let's say, the the two vaccines were, the same effectiveness, they're just as good as each other, then if I do this, if I do the first proportion minus the second proportion, well, if they're the same number, same effective rate, then all of these would be zero. Okay. And so our confidence interval would end up having a negative number here and a positive number here. And so you would say, oh, well, zero is in that range. Okay. So that means there's a chance that they're just, there's no difference. One is just as good as the other. Okay. So that's what's happening here. So Willy Wonka claims that M&Ms and Skittles have slightly different proportions for your color. Okay. So he is saying that they're not the same. He's saying that this one and this one are different, which we believe in. Okay. So does your confidence interval support his claim? Okay. So that depends on whether zero is in the interval or not. Okay. Because if zero is in the interval, then that means there's a chance that the two proportions are the same. So right here is zero. Now for my confidence interval, I have negative 0.11. So I have negative 11. And then I have this one, which is real close to zero, negative 0.00001, but it's not at zero. So my confidence interval is here. It does not contain zero. Okay. So For me, 0 is not contained in the interval, okay? So he is saying that the two proportions are different. And I agree because I'm 86% confident that the true difference is somewhere in this range. And all of these in here are not 0, which means that I think that M&M's has a smaller proportion of green than Skittles, okay? So I support his claim because 0 is not contained in the interval. Now that's for me, okay? If, on the other hand, you have a confidence interval where this one's negative and this one's positive, then that would mean that 0 would be contained in the interval, and that means there is a chance that the two proportions are the same. So in that case, you would say that you do not support him because 0 is in the interval, okay? This is basically hypothesis testing, where we are, he's giving us this claim and he's asking us, to support that claim or not, which is the same as rejecting the null hypothesis or not rejecting the null hypothesis. Okay. These two are very similarly related. Okay. All right. So, uh, your answer is one of those. Right. All right. Next, we're going to look at redoing this and how many if we wanted to redo this to get more accurate, okay? Because I've got a pretty big range. This is 11% down to 0%. So an 11% range is pretty big. So if I wanted to be more accurate, I would need a bigger sample size. How big of a sample size? That's what we're going to look at next. Using your proportions for M&Ms and Skittles for the second largest difference color. So I'm still doing green, okay, for me. Whichever one you circled for number 3. Okay. Uh, as prior estimates, but use confidence level number 2. My confidence level number 2 was 76.3. Oh, that's a crap confidence interval. It's too low. It needs to be in the 90s. All right. 76% confident. Calculate the minimum bag size for each type of candy required to ensure that the difference in proportion of the second largest difference color, so green still, is within a 2% margin of error. Okay. So in other words, I'm looking at this and I have like an 11% margin of error, or I guess it'd be 5%. So uh, close to 6%. Basically, any number between 11% and down to 0.0001, my true proportion is going to land somewhere in this confidence interval. And that's huge. That's a big range. Okay. If I wanted to get more accurate, I would want a smaller confidence interval. So I want to be within a 2% margin of error. So that means I'd be up by 2 or down by 2. So if the true value is 0.3%, I want to have a confidence interval that goes from 5% down to 1%, right? Basically up to and down to, okay? This is a much smaller range. This is only a 4% difference between the top and bottom, okay? So I want to be more accurate is basically what I'm getting at. So to do that, that is on page mm, page 261. Uh, Single population sample size formulas. We don't have a single population. We have double population sample size formula. Okay. So it's at the bottom. It's a little, it's very similar to the single one where p hat, q hat, c alpha over 2, margin of error squared. Okay. It looks crazy though. All it is we added p hat q1, p hat 1 and q hat 1, and then you add p hat 2, q hat 2. You still have the z alpha over 2, and you still have the margin of error, and you still square it. It's just the stuff in front that got a little out of hand. Okay. If you have no prior estimate, you just say, okay, I'm going to use 50% for that, 50% for that, 50% for that, 50% for that. So 50% times itself is 25%. You add those together and you get 50%. So it's the same formula, just using 50% across the board. Okay. All right. So we need the formula, do some substituting, and we'll get our result. Okay. All right. Formula here is n equals. Now, they have a bunch of things here. N equals N1 equals N2 equals the thing. Okay. All that means is when you go back and you redo your sample, you're going to use whatever result you get here for how many M&Ms you need and how many Skittles you need. Okay. It's going to be the same value. In our case, when we did this, we just went and, we selected two bags of M&M or a bag of M&Ms and a bag of Skittles, and we didn't really get to pick how many were in the bag, right? So I had a different value for my sample sizes. This is saying if we go back and do it again, we'll want them to be the same. All right. And then alpha 2 over error squared. Okay. All right. So this will be my M&Ms. This will be my Skittles. Okay. So P hat for M&Ms, I'm still doing green, was 0.152. And Q hat, I had that on the previous page, 0.848 for M&Ms. For Skittles, P hat, 0.212, and Q788. Margin of error was 2%. All right, I need Z alpha over 2. My alpha is, sorry, my confidence interval is 76.3%. So my alpha in this case would be 24%. Half of that would be 12%. So let's come over here to StatCrunch. Let's calculate our Z alpha over 2. So we'll go to Stat, Calculators, Normal. Okay. Stat, Calculators, Normal. Here's our normal curve. We do between. We put in our confidence interval right here, 76.3. That's mine. And that gets me my Z value. Okay. 1.1825. So stat, calculators, normal, and then hit between. This is all the stuff we did in chapter 7, right? All right. Now yours will be different because when you did On page 579, we did confidence level 2. You did a random number, so you got a different one. Okay, that's fine. All right. So now I've got this. I needed to calculate my result. So I'm going to put all this craziness into StatCrunch. The parentheses are all in the right spot for you. So let me do it. It's okay. Do it this way. All right. Times plus times close my parenthesis, open a new parenthesis, 1.1825 divided by 0.02, close my parenthesis and square it by holding Shift 6, 2. And there's my number. I get 1034.58. Okay. All right. Now, what were we doing? We were looking for, I was going to redo this. I want to get more accurate. I want to get a 2% margin of error. How many Skittles and M&Ms do I need? I'm going to need more than I bought the first time. So I'm going to need this number. Now, this is a sample size. Whenever we do sample sizes, we always round up. Okay. So this is not our answer. Our answer is 1,035 M&Ms. And we need 1,035 Skittles. Okay. It's not 1,035 total because I could buy, 500 M&Ms and 500 Skittles. That's not the case, okay? This is saying that N equals N1 and N2, so your sample size has to be 1,035 for both of them, okay? All right. Now, that's not going to be possible, or at least it's going to suck because when I buy a bag of Skittles, I don't get to choose how many are in the bag, right? So how am I going to get exactly 1035? Well, the answer is you don't need exactly that number, okay? If I wanted exact, this is the exact, but we rounded that, okay? We rounded it up because this is actually going to give you a better margin of error. So maybe it's 1.999% margin of error. What I mean by that is this is my minimum, basically. I need to have some number that's bigger than this, and I'll be able to say I'm within a 2% margin of error. So I'll go out and I'll buy a bag of Skittles and I'll count them. And if I only have 1,010, I'll need to buy another small bag and then I'll count them and make sure that I end up over this. So if I end up at 1,050 Skittles, that's fine. I don't need to throw some out, especially since if you do that, you could possibly bias your result. Okay. So anyway, all I'm getting at is this is just a minimum to get what you're looking for. Okay. All right. Let's go on to page 581. And now we'll talk about hypothesis testing. All right. Oh wait, we gotta do this one first. For number 10, suppose when you are doing number 9, you had no prior estimate for the sample proportions. Would your sample size have been smaller, larger, or the same? You guys know the answer to this one, so what do you think? When you use the formula on page 261, There's this one if you have a prior estimate, and this one if you have no prior estimate. Same thing, if you have prior estimates or no prior estimate, one of these gives you a different sample size, or this, or I guess are they could be the same. Are they the same? So what do you think the answer here is for number 10? Take a guess if you're not sure. What do you think the answer is for number 10? Suppose when completing number 9, you had no prior estimates in the sample proportions. Would your sample size have been smaller or larger or the same? What do you think, Elaine?
Well, point 0.5 times point 0.5 is as big as it can get. Because if you go down to point 0.4 times point 0.6, that's 0.24. And I'm saying larger.
Okay. Yeah, so, and you can write that on here if you need to. No prior estimate is always going to give you a larger value than if you have a prior estimate. That's why we use a prior estimate because, smaller sample size is usually easier to handle, so larger. All right. Now, for this next one, it's going to depend on what you had for confidence levels. So for number 9, I had used this confidence level. Suppose you had used confidence level 1 instead. Would your sample size have been larger, smaller, or the same? So in my case, this one is bigger, so that means it would have been larger, okay? On the other hand, if these were flipped, if this one is bigger when you select your random confidence levels, if this one ends up being a larger one, then it's going to be smaller, okay? So depends on what your numbers are for your confidence levels for number 1 and 2, okay? All right. Now let's move on to hypothesis testing. So you want to conduct a hypothesis test for the difference in proportions of M&Ms and Skittles for the largest difference color. So now we're doing the largest. So um, mine was red. Okay, so we're on to part 4, which is our hypothesis testing. So I'm going to be looking at red, and I want to use. Okay, so verify whether all the requirements are satisfied for conducting this test. Okay, so now I looked at green already. I did some confidence interval stuff, but now I want to look at red and I want to say, okay, I want to test whether the proportion of red M&Ms and red Skittles is the same or if it's different. Okay, to do that, I need to first check and make sure that I'm satisfying the requirements for the central limit theorem. So it's going to be very similar to what we did for confidence intervals. Okay, confidence intervals and hypothesis testing are pretty much the same thing, just in you know uh, different steps. So I need to check it's random, independent, also independent of the population, and then normal for both of them. Okay. First of all, random, yes. Every candy had equal chance of being in my bags. Okay, so we're good there. Independent, we have two groups measured once. So we're good there. Okay. Independent of population. So I need to check N, 20N is less than N. M&Ms, that is 145, all M&Ms. So 2900, all M&Ms. So that's exactly the same as what I had before. You check it for Skittles as well. 20 times 241. That is 4820, and that's less than all Skittles. So yes. Okay. So all that is the same as what we did when we were looking um, at confidence intervals. The different part is going to happen here because now I'm not looking at green anymore. I'm looking at red. It's very similar though. P hat, Q hat for this. Let's see, my red P hat was 0.117. So my Q hat then is what? 0.883. All right. And I get 14.9, which is bigger than 10. So we're good there. Do it again over here for Skittles. For red, for me, 0.195 times 805. All right. 7.8 is bigger than 10. So yes. Now your numbers are going to be different, of course. Okay. That's the same concept. All right. We get all yeses, we can move on. But for this particular project, even if you did get a no, that's okay. So we're going to keep going because test whether there's a significant difference between the proportions. Oh, I didn't say regardless of. Okay. Regardless of whether you got any no's. Test whether there is a significant difference between the proportions of M&Ms and Skittles that are the largest difference color. So again, mine's red at a level of significance number 1. So that was, for me, level of significance is 0.017. That's going to be my alpha. Okay. So whatever you had on page 579, whatever you had for your random significance level, okay? So we have our null hypothesis, alternative hypothesis. So your null hypothesis is P1 minus P2 equals 0, okay? Now you can write it that way, okay? You can also write it like this, P1 equals P2, okay? Either way is fine, okay? Because basically, if you just add P2 to both sides, you get P1 equals P2, okay? Right? The null hypothesis is always equal, okay? This part, though, does matter. If you write it like this, okay, you need to make sure you put the greater than, less than the right direction, okay? Now, for me, I'm testing not whether M&M's is higher or Skittles is higher. I'm just seeing if they're different, which means I'm doing a two-tailed test, okay? Which means for that way, case, doesn't matter which order these are in, okay? All right. Anyway, now that I have that, got my alpha already. Step 3, we're going to uh, find the z statistic. Unlike the hypothesis testing we did in chapter 10, where we wrote out the formula and then we did some substitution, um, we're not going to write out the formula for when we have two different independent populations, just because it's pretty complicated. Okay, I mean it's nothing that you guys can't handle. It's just a little long. So it's very similar to what we did in chapter 10. So if you understand what we did in chapter 10, then you're going to understand that formula as well. So it's not really worth, getting into. So we'll get that from the StatCrunch. Okay. So that's going to be under stat, proportion stats, to sample with summary. Okay. Which is the same thing we did for hypothesis testing, which is fine. So let me close this. Stat, proportion stats, two sample because we have M&Ms and Skittles. We have two different samples. With summary, I'm doing red this time. 17, 45 still, 47, 241. Uh, leave it as hypothesis testing. And most of the time, when we're doing hypothesis testing, we're comparing whether the two populations are different. Okay. We're comparing whether the two different vaccines, which one is better. Okay. How much better does it need to be? It doesn't matter. Okay. If it's just slightly better, that's good enough to say, okay, let's use this one. But sometimes you do need to be able to say, like, okay, if this vaccine is like 10% better than, the other one, don't even use the ineffective one. Because you'll remember when, the COVID vaccine started being given, there were multiple ones and everybody was using all of them, even though it was possible to figure out which one was better. It wasn't so much better that like the other one was just useless, right? So anyway, what I'm getting at is most of the time we're going to leave this as a 0. It's going to be very rare that we would change that. Okay. But for this part, we are doing not equals, and we want to show our critical value, or no, it's going to give it to us. So don't do that. So just hit compute. There we go. Um, oh no, I do need that. I need my z stat. There it is. That's what I need. So that's my z0. Negative 1.98 9. So real close to 2. So you'll remember that when your z value is close to 2, your p value is going to be close to 5%. And that's what mine is in this case. It's close to 5, 0.466. And it's a two-tail test. So I'm shading both sides of my curve. Right? So these two values add up to 4.6%. So these two values, this one's going to be 2.3, this one's going to be 2.3. So, all right. Step 5, we're going to compare our p-value and our alpha. 7. And this is not the right one, right? Step 5, if your p-value is less than alpha, you reject it. So do not reject our null hypothesis. State the conclusion. There is not sufficient evidence. So you can't just say there's not sufficient evidence to support the claim. You can't just say support the claim or don't support the claim. I had a couple of people try to turn that in. You have to write out what the claim is, okay? The whole point of step 6 is to explain this to a person. That's why we're writing it out as a sentence, okay? All this up here is math and complicated graphs and crazy stuff, right? This is not what you would present to, your leadership when they ask you to test something. You present your results down here, and then if they ask, how did you get to that, then you can show the math and explain it, okay? But sometimes there are, when you do a test, like people don't want to see the math. They just want to know the answer. Was it better or was it not? Was it the same? Was it different? Okay. So you got to write out what the claim was. The claim was that M&Ms and Skittles have different proportions for red. Okay. There is not sufficient evidence to support the claim that M&Ms and Skittles have different proportions for red. Okay. Maybe I could word that a little bit better, but that's basically what we're showing here. Now, I will point out that earlier, when we were looking at confidence intervals, Willy Wonka, he was saying that they have significant differences, and I supported that claim. But now I'm changing my mind and saying that there's not sufficient evidence to support that they're different. So why did I change my mind? What happened? Well, the difference is in which alpha I'm using. Okay. Here, I'm looking at an alpha of 1%, 1.7. That means I'm looking at a confidence level of 99% or 98.3%. Okay. So that's a very high confidence level. When I was looking at uh, confidence interval here, I was looking at a 76% confidence interval, okay, which is not that high of a confidence level. So I was able to support that claim because I had a huge alpha. Okay. So if I had a huge alpha for this case, right, my p-value was 4%, 5%. Okay. If my alpha had been much higher, this would have been less, and then I would have been able to reject the null hypothesis. But I also would have been, at risk of making a type 1 error, or at least more of it. Okay. So all that to say is the reason why, I agreed with that they were different proportions earlier and now I'm not is because um, I was 76% confident. I was kind of confident. But if you asked me, no, 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 I don't need you to be kind of confident. I need you to be very confident. That's going to change my answer. And I'll be like, I don't know if I have enough data to be very confident. Okay. So anyway, that's where the difference comes in. So okay, that's all for the Chapter 11 project. We're not going to end yet. I had one more thing we're going to talk about. So, next week we're going to start looking at the sample final exam. But actually, we've already started looking at it. We looked at page 1. We're going to look at page 2 of the sample final exam because the sample final exam is pretty big. It's 14 pages, and we're going to talk about it on Tuesday next week. But we're probably not going to have time to go through the entire thing on Tuesday next week. So some of the pages, Elaine and Cindy will work with you guys on Monday and Wednesday next week. Um, but part of the reason why, the sample final exam is so big is we've talked about a lot. This class covers a lot of material, okay? Also, the final exam is a little bit longer than the midterm. The midterm, you'll remember, was 9 pages. The final exam is 12 pages, okay? So again, if you ran out of time on the midterm, or you were close to running out of time on the midterm, you should definitely consider taking it at the testing center for the final exam because final exam is going to be a little bit longer, okay? But it's going to be the same amount of time. So I'm still only, going to be on Zoom for 3 hours. So if you run out of time, I don't want you to have to turn in some questions that are blank. So, all right, let's look at page 606. We're going to look at question number 2 on page 606 for the sample final exam. A country's gross domestic product is an economic measure of how much stuff the country produces. So GDP, it's measured in dollars, but that's not necessarily like, the country didn't necessarily make that much money. It's just, when you produce something, you could sell it. How much is it worth? That's how GDP works, right? Um, Carbon dioxide, CO2, is a greenhouse gas that contributes to climate change, often produced by humans. The scatter plot here shows the relationship between GDP in dollars per person and the CO2 emissions in pounds per person for a random sample of countries in the year 2018. Okay, so we did a linear regression on here. Okay, which variable is the explanatory variable? So that's the x-axis. So that's GDP. Which variable is the response variable? That's your y values, CO2. That's your dependent variable, CO2 emissions, okay? How many countries were sampled? So they've done the StatCrunch for us. So sample size here was 47. All right. What is the strength of the linear relationship between the two variables? So that's going to be based off of the R value, the correlation coefficient. So strong positive, moderate positive, weak negative, which one is it? So um on test day, so if today was test day, I don't want to have to be flipping through my exam notes trying to find this, right? So it might be a good idea to write down which page you'd want to be looking for this information. So I'm going to ask you guys, which page would I look for linear regression when I'm, on test day and I'm looking at my exam notes packet, right? what page would I find that there's a number line, right? That had where strong positive is, strong negative. Thank you, Andrew. Page 255. Yep. Page 255. This is all the chapter 4 linear regression stuff. They've already done the stat regression simply linear. They already did the stat crunch for us and got the results. But here is our number line, and we are looking at an R value of 0.85. So 0.8 is right here, 0.85 is in the strong positive area. And that makes sense, right? Because basically, if you make a lot of stuff, you're probably going to produce more CO2, right? If your country produces a lot, they have a lot of factories, um, or even if they don't have factories, even if it's just farming, tractors produce CO2, so you're going to be producing more CO2 in your country if you produce more things. That's generally true. It's not 100%, it's not perfectly on the line, right? There's other factors, right? There's lurking variables. But anyway, interpret the coefficient of determination in the context of the situation. That's here. Formal interpretation of the coefficient of determination. So all this stuff's on page 255. Now, we write out the r squared as the percent. So not this one. We write out the r squared as a percent. 72.9% of the total variation and then we write out the y variable, CO2 emissions, is explained by least squares regression line. All right. Write the regression equation. So they gave it to us here. CO2 emissions equals this number plus this number times GDP. I'm going to use X's and Y's for that. Okay. And I switch the order. You don't have to switch the order. You can write the 211 first. It's up to you. What is the slope of the linear regression? So the slope is the number attached to the x, 0.496. Interpret the slope in the context of the situation. So that interpretation for the slope is here. If x increases by 1 unit, then y is expected to increase or decrease by approximately slope units. If x increases by 1, and then the unit of x is dollars per person. $1 per person. And y is expected to, and then we would write increase if it's positive, decrease if it's negative by approximately. Write the slope out, and then you write the units for y, which is pounds per person. If GDP increases by $1 per person, then CO2 emissions is expected to increase by approximately 0.496 pounds per person. What is the y-intercept? That's the number that's not attached to X 211.4. Explain why this likely does not make sense in the context of the situation. So they added likely, which is different from previously. But so this is saying if your GDP for your country is zero, then your CO2 emissions are 211 pounds per person. Okay. That doesn't make any sense because, first of all, if your GDP is zero, that means your country does nothing. Your country doesn't produce anything. You just have a country of people sitting around sitting around at home. Okay. That's not possible. If that was the case, you didn't have a country. Impossible for a country to have zero GDP, right? The other thing is if your country's sitting around doing nothing, then 211 pounds per person for CO2 emissions. I guess they're just breathing. You're just sitting around breathing 211 pounds of carbon each year. Seems like a lot to breathe. All right. For the US, X is 61,400. This is how much money each person produces, $61,000 per year. Obviously, uh, you're not getting paid that much, right? When your boss, if you worked at like a factory or wherever and you made this much money for your company, your boss is going to pay you part of that, and the rest is profit for the company, right? I don't know how that makes you feel, but you are you get paid less than what you produce. That's just how, you know, otherwise if you got paid more than you produce, that company would be losing money, right? So okay, find y. All right, y equals, we'll plug in our x, 61,400, 211.4. Okay. 496 times 6,100, 211.4, 30,665.8. All right, what does all this mean? Explain what these values mean. So the US has a GDP of $61,400 per person. So that's how much each person produces each year. And produces CO2 emissions of 30,665.8 pounds of CO2 per person each year. Okay, that's how much each of you is putting into the atmosphere. 30,000 pounds of CO2. Seems like a lot. Okay. US has a GDP of this per person and produces CO2 emissions of that per person. All right. We're going to stop here for the day. So we'll work more on the sample final exam on Thursday. We'll also do the chapter 11 review. And if you have any questions, feel free to stick around. Otherwise, I'll talk to you later. Elaine, I do have stuff for you, so don't drop off yet.
Okay, I'm here.